Okay, if you're tempted to run screaming into the night, instead run screaming to the video entitled Standardized Variables. This is going to spook some people. Don't worry about it, I'm just standardizing. The variables x and y. Now you're back. So you can see here I'm just subtracting out the mean and dividing by the standard deviation of y. Same here, this is an x. Subtracting out x mean divided by creating z-scores, z's, for each of the two variables. As an easier way, there's a complicated formula for the correlation coefficient that if you force me to, I'll show it to you in person. It's easier to think of. I want to standardize both these variables, then run the regression. Notice that I put a tilde on top of these two things, and I just got a sigma on something different other than error. But you do the same thing, ordinary least squares, regression on standardized variables, and you get a statistic that has a more elaborate formula, which again I may show in class or I may not, and there are 2 or 3 different ways to state the formula. That's all that I'm doing here, and then over here I'm gathering up terms. So this video is to expand our sort of use of parameters that we find in the linear regression model with 2 variables, one x and one y, and to add some things. So first we know A is the estimated intercept. This is from the regression of just x on y. And B is the estimated slope, or often referred to as the estimated regression coefficient. And then from the last video, SED is the standard error of the estimated regression coefficient, and the ratio of the coefficient to its standard error defines T. Once more, you're looking for something about equal 2.0 or greater. That will have then associated with it a p-value. The p-value in this context is the same definitionally as it has been in other contexts. The p-value is telling us the probability that we would find as extreme a value as the one we observe for B if we continue to sample over and over and over again with the same sample size, and the null hypothesis was true. The null hypothesis being that the slope coefficient equals 0. And so it gets small underneath 0.05 when it becomes a reliable statement that we're pretty sure that in repeated samples we'll find a B as extreme as the one we've observed. Now we're down to here and here. So as it turns out, if you run this regression, I'll have you do it in class. You're going to see that A falls out. So a standardized variable regressed on another standardized variable is going to have an intercept of 0. These things have mean 0, standard deviation of 1. The coefficient here, B now, is going to be something really important, really strong, and used all the time in social science research, and used even in common everyday language. It's the correlation between x and y, denoted small letter r and then the subscript xy. The correlation coefficient, there are different, I'll show you another way, rx and y. Correlation coefficient is intimately related to the regression results. It is the estimated coefficient, not the standardized thing, the estimated coefficient weighted by the ratio of the standard deviations of the 2 variables, standard deviation of x over the standard deviation of y. It is a measure of association. It is more specifically a measure of the linear association of two variables, and still we're assuming an x and a y that are at a ratio in a / interval. Although correlation coefficient is used routinely to describe the relationship between 2 dichotomous variables. It's used routinely to describe the relationship between an ordinal variable and another ordinal variable, an ordinal variable and an interval variable, on and on and on. This is a widely used, the most widely used measure of association. The one place that it'll completely fail you is if you have 2 multi-category, or even one, or two multi-category nominal level measures. Otherwise, it's used and abused routinely everywhere. The correlation coefficient cannot go below -1, and it cannot go above +1. And the correlation coefficient of 0 indicates no linear relationship between the two variables at all. Correlation coefficient near 1 or at 1 means that the two variables are perfect linear combinations of each other in a positive way. As one goes up, the other goes up. A negative correlation means that as one of the variables goes up, the other one goes down. So the negative is given simply by the sign of the coefficient, which is the direction of the slope of the line. That being a negative slope, that's positive slope. Correlation coefficients are ubiquitous in the social sciences. We say these two things are correlated. Refers, at least technically, to this coefficient, which was brought into use by the statistician. I don't even say his name. It's been in use for over 100 years. So we say two things are highly correlated when either on the positive side or the negative side there's a substantial difference between the coefficient that we find and 0, right? Correlation coefficient. R squared, another thing you need to know. In the bivariate case, and we're in the bivariate case because we're going to go to a separate video for multivariate regression. So be clear that these definitions don't hold in the multivariate case. But in the bivariate case, all this becomes very easy. So the correlation coefficient is just the regression coefficient weighted by standard deviations of the two variables, or as introduced earlier. And R squared is just the square of it. So down here it says equal R squared. In the bivariate case, write that down. In the bivariate case, 1x, 1y, R squared is the square of the correlation coefficient. I should say his name. Carl Pearson is the statistician responsible for developing the correlation coefficient. And this, I say his name because sometimes this is called Pearson's R. Write that down. Pearson's R, the correlation coefficient. Relative to measures of association seen before, I haven't done that video yet, and I'm running out of time. So by seeing before, that could have been in person with me, or it could be a video. Probably a brief one, because I hate measures of association other than Pearson's R, except ones that I make up myself, and we're not going to teach those in the basic class. This is really neat coefficient. It's a neat measure of association because when we developed measure of association, did so because we looked at chi-square, and so it tells us the statistical significance of a departure from independence, but it doesn't tell us anything about the nature of the relationship between two variables. It doesn't tell us anything about the strength. Pearson's correlation coefficient has it all. It varies. It gets close to 1 or -1 when the relationship is strong. It gets close to 0 when it's weak, right? And because it is a function of the regression coefficient, you could turn right here and find out whether the result you're observing is statistically significant in the common parlance. So we'll see a lot of those in class, including a matrix of them. R squared, the square of the Pearson correlation coefficient, has yet another meaning that gets back into, I keep this Campbell thing hovering over me here. John Stuart Mill is their source. R squared has another interpretation. It's the percent of the variance in y explained by x, explained by the variance in x. Percent of the variance in y explained by the variance in x. I'm going to illustrate that for you, and then you're going to be able to draw this yourself on a test. It says, show me a negative slope and a high R square. Show me a positive slope and a low R square. We're going to do positive slopes first and just do high R squared and low R squared, and put the points around them. These slopes, might not be technically But I intend them to be the same. Let's say the slopes are 1, both. And so you have two problems here, say two populations. But you're using the same variables, x and y, whatever they are. So this is a high R squared. Recall the definition of error in the equation is the distance between the points where they actually reside and the point on the line that will correspond to that point. And we see here a really tight grouping of the points around the line. Now consider the same variables. Here for the regression slope estimate, you're going to get the same thing across both problems. So the regression slope is going to be 1. And yet these are two very different relationships. They're identical in terms of the sign. As x goes up, y goes up. They're identical in terms of the slope. As x goes up 1 unit, y tends to, on average, go up 1 unit. But they're fundamentally different relative to the strength of the linear relationship between the two. You've already guessed, this is the really strong relationship, super strong. And this is the much, by comparison, weaker relationship. Again, let's assume all the x's and the y's are measured on the same metric and that all of them are ratio level. In this circumstance, the correlation between x and y is going to be super high. And likewise, the square of it, r squared, the percent of the variance explained in y, is going to be high. And in this circumstance, despite equal A and equal B, equal intercept and equal slope, in this circumstance the r squared is going to be much lower, and likewise the correlation coefficient is going to be lower and closer to 0. So you can evaluate then using the bivariate regression model, using ordinary least squares to estimate the parameters of the model. You can use that information to say a whole heck of a lot about the relationship between these two variables. This is limited right now to 2 variables, and limited right now to we'll assume ratio level measurement on both sides, x and y. But as we'll see in coming videos, this logic is extendable to all kinds of levels of measurement on the right-hand side of the equation among the x's. And then as we'll see at the very end, the logic can also be extended as long as we are willing to use another estimator other than least squares to left-hand side variables, that is y variables, that are measured at lower levels as well. This is powerful stuff. This is getting toward the end here. We're looking at the correlation between an x and y, jumping through hoop number 1 and saying these two things are related in a linear way. Here's how, here's in what direction, here's how strong, and this is the parlance. So, on now.